So first, let's go through a brief history of autonomous driving, right? It started way back in
The direction the keywords are
90s.
pointing may also be controlled by computers. In 1987, VAMORS demonstrated worldwide top performance on a new stretch of Autobahn not yet turned over to the public. It cruised at various speeds with
So if
top
you see,
speed of
they've
96
implemented a
kilometers per hour,
rudimentary
limited only by engine
computer
speeds,
vision algorithm
over a
and a
distance
control
of more
algorithm.
than
It
20
was back in
kilometers.
1986. They
Since
had most
1989,
of the
it
L2
has also
features
been possible to
that is there in
recognize
modern cars,
obstacles.
even at that time, but they
As
didn't.
a
It was a
consequence,
research
it has been
project, right?
possible to achieve the transition into a convoy driving mode. Since the early 1990s, it has also been possible to perform lane changes autonomously.
And they
In
put all these state-of-the-art
1993-94, in the framework
computers
of the
which are like
third
very
phase of the
big
Eureka
in the back of
project,
the car,
Prometheus,
and then
three
they made it
Mercedes-Benz
real time.
S-Class passenger
And
cars were
this was
equipped with
actually driving in
University
the streets in
Bundeswehr
the
vision
highways of
systems,
Germany, and it
based
was able
on
to
new
track six
micro-miniaturized
cars at a
TV
time and then
cameras.
make decisions, right? And it was using
All electronic
rudimentary
equipment now fits
lane
into the
detection
trunk
to
space
center the
in
car in
order
the
to
lane,
achieve better
right?
maintainability and accessibility.
So this was back then in 1986. And then way over here around 2012, we had first commercial L1 and L2 cars also by Mercedes and Media and BMW. They had autonomous braking and those kind of things, autonomous lane keep assist. These all came in 2012, and then 2015 we had Tesla, which kind of made this mainstream. They called this autopilot. They called it self-driving cars, which are more understandable to the uh, big population, the mass people. And eventually we have things like Waymo in 2016, right? So we have different level of autonomous driving. Level one is just the longitudinal control. Level two is also the horizontal latitudinal control, like steering. It also adds to the steering. And level three is most of the modern self-driving cars, where cars can take care of most of the things, where the user um, doesn't have to take user has to be sitting on the driver's seat, but they don't have to pay attention. Level 4 is where user doesn't have to be sitting on the front of the car. They can be sitting in the sitting behind, and the car will take care of most of the things. That's what's happening in Waymo right now. And level 5 is where this is not constrained by geography. That's where Miss Tina actually talked about. So we have these 5 levels. We are currently maximum at level 4, which is geo-fenced, right? Then we'll try to discern 5 different steps in self-driving cars in a modular architecture. First, we have perception, localization, then prediction of other things, and then planning, and then eventually control, right? So first, let's go to the perception part. So there are a lot of challenges in the perception, because road is a very dynamic environment. For example, here the car has to not obey the lane so that it doesn't crash on the cones and the construction site, right? You have trees, you have you have traffic signs, you have things written on the road which says something to do, right? And there's also more different classes of things. Like, it's a very big challenge. You have cars, you have different types of cars which are coming out, you have trucks, and you have cycles mounted on cars. Like, you have the cycle and car is generally two different classes in a perception algorithm. And you have cars on top of trucks. Again, it's confusing, right? So is this one car, two car, or car on top of another? Your perception there's a lot of ways in which you can confuse your perception algorithm, and it has to be robust, right? And here, speed signs, this is a very big nightmare. We in modular systems, we have a separate ECU and a separate unit which talks about speed signs, like signs and then traffic signs. uh, For example, you have things like speed should be 9.5, speed limit is only 25 miles per hour during these times, and only on school days, right? And yeah, speed solving speed science and then traffic science itself is a very big problem, right? And then so how can we need a, like Tina ma'am first said, we need a robust data set for all these things, and we need different data sets for different geographic locations, because all these standards change in geographic locations. So we need to train different models, and then we need to have different weights for each geographic location, right? Within these submodules. So this is where data engine comes from. This is one from Tesla, but many companies have a similar data engine where we first develop these models and then have a closed fleet which moves in the cities with a test driver, and then we see where in this fleet, in which situations and which scenarios does this algorithms fail. And then we take all these scenarios, and then we try to recreate it in the simulation. We try to collect a lot of data in these particular scenarios, and then we retrain the model, and then we again deploy it, right? This cycle goes on and on until you perfected this machine learning model, and your the amount of error rate is very less, right? So let's see what kind of sensors we have for this kind of perception. First, we have cameras, like convolutional neural networks, if it's a modular system, and we have multiple cameras. This is like three cameras facing front, and we normally have three cameras also facing back. We have radars. So this is a radar ping, which you generally see in an autonomous car. And if you observe this, radars are very good at mapping distance, but the pixels are like the resolution is not very good, right? It's like a cloudy picture. And then we have a lidar, which has very good resolution, but the its frequency is very less because it needs a lot of processing to process a lidar image. If you get like 100 frames per second in an image, in your in a vision based system, in a lidar based in your lidar sensor, you'll get maybe 30 or 40 snapshots per second. So you need to sync all these things, right? So each one of these sensors have their own set of advantages and disadvantages. So you need to fuse all these to make the best possible guess of the environment around you and where you are currently in, right? And there are two different methods. You can fuse all the LiDARs and radar, all the different types of sensors, or you can just use vision-based systems like Tesla does, right? In case of Tesla, it's a distillation process. Actually, while training, they use radar, LiDAR, as well as vision to create the training and then classification. So they take this robust system, which is very accurate, and then they train the vision model based on the data which is generated by this. So this is a type of distillation where you take a bigger model and then generate the results, and then take these data pairs and then try to train a constrained model. Like it could be constrained by sensor input or the model parameters, and try to imitate what this bigger model does, right? So that's what Tesla does. So while training, they use all the LiDAR and radar and camera system, multi-sensor system, but during inference, they use only the cameras. So most Tesla vehicles just have the camera-based application, right? So when you distill, you reduce the cost in inferencing. So when you sell to customers, the only problem they have is inferencing, right? So you don't have to invest a big LiDAR system and a big computer system. You can just have the um, computer vision based system, right? This was done also in DeepSeek. For example, they trained a bigger model and then they tried to distill it to a smaller model. They tried to make a smaller model imitate this bigger model, so that while inference, you just use the smaller model because it uses less compute, right? So once you got all these things, all the detections happened in these individual sensor modules and their compute modules. Now you have your camera says there's a person over there in this bearing, and then radar says a person is there in this bearing and this much distance. Your LiDAR gives a more higher definition of this. You take all these things and then you fuse it in something like a Kalman filter, right? So all the sensor inputs, detection inputs come, and then there's a fusion algorithm, fusion module, which uses a Kalman filter to fuse to make the best guess of the environment given all these inputs. So after fusion, this is what you get. You get something like this. Green is your car, and as you see, the radius of detection moves along with this car, right? So it has this, it tries to put itself in the map and then tries to map everything else after fusion. Okay, this is where the other car is, this is what its velocity and so on. So, okay, you did your sensor fusion. What is next? Next is localization. You need to know where in your map you are currently at. So have you experienced it before when you used Google Maps and your compass didn't work? You know where you are, but you're not able to decide whether to go in this direction or this direction because your compass is not working. So that's a localization problem in real life with humans. So same thing happens with cars. It's not just you're aware of your surroundings. You need to know what state you're in given a map. That's that's when you can decide whether to take left or right, whether to go forward or reverse, right? Based on your overall mission plan, overall destination. Otherwise, things might, otherwise, even if you're aware of your surroundings, you may still end up in something like this, right? This is a very good meme. Yeah. So that's where localization comes in. You need to, you first represented your scene, but then you need to localize yourself. What's your current velocity? What's your current bearing? And where in the map and you are located, what's your orientation with respect to the map? And this along with map parameters. So in say self-driving cars, we have parameters embedded within the map. You can see these small lines on this map. It says the speed limit for that particular road, particular lane, whether you can take left or not. So all these hyperparameters will be embedded in that map. It will place your car on that, and this gives a constrained set of problems your car has to face now. It should go within this speed, and then there's an intersection ahead. You can take left according to the traffic rule and so on, right? So localization is done. What next? You need to constrain your problem even more. So that's where occupancy map comes in. So what you do is there are immovable elements within the road, right? So buildings are immovable, parked cars are immovable, and when there is an immovable element in the ground level, you necessarily don't have to plan your path uh, through those immovable elements. So you can constrain your map even more, and then make this blue region where your planning algorithm has to worry about. Your path planning algorithm can remove all these, can ignore all these regions where the immovable buildings and trees and parked cars are there, so that um, your planning space is more constrained and you have a better algorithm. Okay, let's go to prediction. So now you know where you are, you know your road, you know where you want to plan your path. Now, what others are doing, right? What others are planning, right? Before planning, you need to know what others are planning. So this is the prediction algorithm. So it predicts what other actors' trajectories are going to be. For example, um, this you can see this prediction algorithm predicting the next 5 timestamps where this other actors are going to be. For example, you see this cyclist where it predicts what the cyclist trajectory is going to be so that your car can plan around that trajectory and not hit the cyclist, right? Next is the decision making. So now you know your current state and bearing, you know where others are, you know what, you kind of have a very good estimate of what others are planning to do. Now you plan what you have to do, right? So this is where your path planning comes in. Path planning is a multidimensional problem, and in a modular system, most of these things are modularized. Like there are different modules to do different things. Like for longitudinal planning, you have lane follow assist, and then lane keep assist, and so on, cruise control, and so on. For lateral planning, you have lane change assist. And so on, like intersection planning assist, and so on. So depending on where the car is right now, the different driving algorithm will get activated, and then it will do that particular maneuver for the car, right? So this is the main planner. This is like the brain, and we also need a spinal cord, right? What if this main planner does something bad? We don't want it to hit a pedestrian by mistake. So that's where it's like this toxic PhD supervisor who tries to monitor everything, toxic manager who sees everything and then stops you, like kind of stops you at the when you do something bad, right? So it treats the machine learning self-driving algorithm as just another driver, and if it sees any course of collision, for example, if your main driver, if your self-driving algorithm inadvertently would collide with a pedestrian, if it predicts that the time to collision is less than 0.5 seconds, it will just go and do the emergency braking. So there's always uh, an algorithm which supervises it and then tries to brake if something goes out of parameters, right? So let's recap what we all these things. First, you have this car which doesn't know where it is. So first, it needs to do sensor fusion to know what others are doing and what the map is, right? And then it needs to localize and then occlude the things which it doesn't have to plan on, right? So now what else it can do? So it has the overall mission plan. So you put a destination to a particular place. So according to the mission plan, it just has to go through this particular tunnel, and it just has to plan through this particular tunnel. So now we have a very constrained problem, and it has to stay in this particular line. It doesn't have to worry about anything else, right? But still, you have one more problem, which is you have other actors. You need to know what they are trying to do, kind of have an estimate of their trajectories so that you can plan around those trajectories, right? So once you've done all these things, you can actually optimize a trajectory for your own car. So what are the different kinds of uh, planning algorithms? There are different planning algorithms. Once you've constrained your problem this much, planning becomes very easy. You can use a very rudimentary approach like RRT. For example, if you once we've done all these constraints, RRT itself can do a path planning very well, right? But there are many more advanced algorithms which are used in self-driving cars. Okay, then comes control. Control is a very vast subject. It goes into EC and robotics. Yeah, to keep it short, just make sure your actuators, your steering motors, and everything is working correctly so that your car takes the correct trajectory. I mean, your car drives through the planned trajectory, right? So this is what it looks like when everything works well. So it has this uh, rose tunnel where it needs to do the path planning, and then it plans through that. Um, yeah, so there are different architectures. One is just talked about is modular architecture. You can have different teams working on different things. They don't have to worry about other modules. Like there can be a perception team working on perception and so on. But the thing is, its limitation. Only limitation is it can't be very robust. Like it's um, uh, there is advantages, like you can debug things very well. Like if something goes wrong, you can pinpoint where it goes wrong. Is it going wrong in perception module, or is it going wrong in planning module? But uh, if there is a error which happens in perception modules, it may cascade onto other modules. That's a problem in this modular architecture, and it's also very big to maintain, even though it's manageable, right? There's also something called end-to-end architecture, which many people are trying to implement. So when you have a sensor data and map, there's a very big model, and it outputs controls for the car to take, right? So it does everything from perception to planning all within itself. The good thing is that it's very easy to implement. Like you can take a game like GTA and then try to build your own CNN model and then train it on that game, and then you can see it works well, right? You can do it in your backyard. You can train it with a toy car. But the problem is it's hard to debug, right? And it's very unreliable. You don't know if maybe your data set is very small, you don't know where this model will fail, or where it will take a very adversarial decision, where it will uh, collide with a pedestrian, for example. So it's hard to debug. If it does something wrong, you don't know which layer, which weights are responsible for that behavior, that wrong behavior, right? Debugging is very hard. So that's why it's not used currently in many applications. There is one real life application where it's used. A company called Wave in London is currently testing it. They are not using it in real life, but yeah, they are testing it. And what they are doing is you have these CNN layers, and then they are actually visualizing each layer, right? And then seeing what neurons are getting activated, and that way uh, they can backtrack and then see what weights are actually responsible for each decision, right? So this is something which is coming up. So you can this is for example one of the MIT's variational model, which is end to end. If you want, you can go through it, you can implement it yourself, right? Then comes safety. This is where data science comes mostly. For example, safety is very important. You would have seen Boeing's one. Things should be very redundant. If you have seen the series, only one sensor, which is the air velocity sensor, if it got blocked, and then it eventually led to two crashes in a big plane. That sensor is the size of a pencil, right? If things are not that redundant, if you don't catch errors in time, it might lead to a lot of deaths. Same thing happens in self-driving cars, because once we release a car, there are millions or billions of cars of that model which will be on the road, right? Especially for a famous company like Mahindra or Mercedes or Tata, for example. There are millions of cars in the road, and let's say the probability of a particular feature failing is like 0.0001. It will still end up being hundreds of accidents on a particular day, because the number of cars on a particular day on the road is very high. So in the self-driving car industry, we call it Six Sigma error, which is very unique to the industry because of the sheer number of cars which are on the roads. So you should have like 0.0006 zeros and then 1% of the error. That's something that's acceptable. Anything less than that error is not acceptable, because you might have one or two accidents every day, right? Even if your error is too high. So what will you do? Like, how will you calculate this risk probability, so that you ensure that it's very low? It's Six Sigma low. So you do that by driving these cars in diverse environments for millions of miles, and then computing the probability. That's the only way to make sure you're highly confident that errors won't happen, right? So for that, simulations are very important. If you make a fleet and then drive these millions of miles physically, it will take, for example, 500 years for validating a particular feature. given the billions of miles you have to drive to validate it. So that's where simulations come in. So we have simulations like this is Nvidia Drive Sim. It looks almost real world, right? So we have put the um, configuration files for each of the sensors. For in this instance, it's the camera sensor, and it actually recreates the inputs by these sensors, and then puts the whole system in a simulation, and then tries to see where the system fails. We also have so we create scenarios like a Monte Carlo simulation. There are random parameters like location on the map for the same setting, and then different velocities. For example, this is a lane intersection scenario. So there are like hundreds of scenarios with different parameters which are being simulated, so that we cover the whole set of possibilities. We also have something called adversarial scenarios, where we have actors and like, have you seen Matrix? So there is an agent which becomes adversarial. So that agent is randomly chosen from the population, right? So similar thing happens. We let the world run in simulation, and then we choose one adversarial actor, right? And then that actor tries to go and then crash with your testing vehicle, and then we see how your testing vehicle evades that, right? So it could be a pedestrian or it could be another vehicle in the road, right? So this is, for example, a demo by Nvidia. So they made this vehicle crash. It's a normal scenario, but then they chose this car to be adversarial, and then it tried to crash with that vehicle, right?
Starts from a
So
recorded clip of traffic motion without any unusual incidents, as shown here. It then automatically selects and modifies the trajectory of all agents, such as vehicles and pedestrians, to generate a collision. Finally, Strive checks if there's a maneuver the Eagle car could have used to avoid the collision, to ensure the generated scenario is useful for improving the AV's planner. We leverage Strive to modify a reconstructed scenario in Nvidia Drive Sim for closed-loop testing. The Eagle car is highlighted in green, and you can see that initially, surrounding traffic behaves normally as shown in the original recording. Now, what if we modify the scenario so there's a collision between the Eagle car and the highlighted adversarial car? Here, Strive automatically generates an alternate scenario where an adversarial vehicle runs the red light and collides with the Eagle car.
So yeah, so this is where this ends, right? So there's a lot of simulations itself is a very data science intensive task where you validate a particular algorithm before it gets released, especially in something like autonomous driving. Yeah, so this is where we are now. For example, Waymo, it's almost in level 4. It can plan very diverse environments, For example, this is the fused data from the LiDAR systems they have. You can see how it plans around a particular place, right? So this is where the industry is right now. And yeah, that's where my presentation ends. And I if you have any questions, you can ask now. I hope there is some time, yeah, for questions. There's already a question from Randir, Randir Kumar. How will we ensure and evaluate the performance of an autonomous driving system in a simulated environment? I think you asked this question before I walked through simulations. I hope you got your answer now. Yeah? Yes, Randir? I hope it did.
But yeah, you can always connect with Neeraj through LinkedIn, I think.
Yeah, please, if you want, reach out. Feel free to reach out to me if you need any clarifications or any doubts or anything regarding your career planning, or if you need any help down the line. Yeah. Thank you, Tina,
Um,
for this
Neeraj,
opportunity.
I have one or two
Yeah,
more questions.
yeah.
You talked about machine learning algorithms which companies use in path planning and trajectory planning. So are they
Yes,
same which we read in the books, or there are some more, some improvisations in those
yes.
algorithms?
In industry, it's always like there is something. which is customized. That's what I've learned in the industry. It won't be exactly what you read in the books. Maybe there'll be a 70% resemblance, but as I told, right, they'll see these bugs prop up and then they'll try to debug it. In that process, they will eventually modify all these things, and they will try to do something patentable instead of because most of these algorithms comes with a license, which would state that it should be open sourced. Any modifications of it should be open sourced and should be available to the community. But it won't be feasible in a industry setting, especially in a self-driving car setting, because of safety concerns and security concerns and so on. So
Yeah.
yeah, industries try to make a customized algorithm based on the car model and then constraints they have.
Okay, got it, got it. So, just a like a normal question. During your graduation time, were you clear in your mindset that you want to go in software field or in data science field or like in architecture, you want to go in the core field? You were also confused, like most of the students are.
Yes. Like I told, I was very confused. Like initially, I was going with a very broad set of things. I was attending product management interviews, UI UX interviews, software development interviews, data science interviews, and then I spoke to people. You eventually need to optimize your industry strategy for you need to converge a little bit. It's too broad that don't make it too broad also. That's what I learned in first half of
Mm,
the interview cycle. And then I converged it a little bit, not too much, but little bit. And I started doing data science and software engineering interviews more. And that's how I landed my first job um, in design direction and product management. Yeah,
okay.
it's better to have not too broad of a thing, but also not too narrow of a thing, right? Of
Mhm.
a domain. Like keep it flexible and keep the window wide enough. Yeah, you can think, okay, I'll go to somewhere technical data science related. So that's a good vision to have. Instead of saying, I'll do data science in medical industry, in medical robotics only. I won't accept any other job offer. So then you're limiting the number of interviews you can give, and you're going very niche. Yeah.
Yes, you're right, Neeraj. So, like you were a average student or a student with getting A plus grades in every every subject? Just like a general question.
I think I'm an average student. I think. Yeah, it was college life was like fluctuating a lot. And my first
Yeah.
year, I was trying a lot of things. Like I showed you aerial robotics from swimming to design studio. So my grades tanked. I was around 7.3 something. And then
Yeah.
I realized in placements, these guys put 8 minimum sometimes or 7.5 minimum. And then
Mm.
I, tr- I did some hard work to keep it above 8 eventually. But yeah,
Oh.
grades don't matter that much, but it matters in your first two jobs at least. They tend to unfortunately see grades in at least early in the career. That's what I felt.
Yeah. Just like in academics, if I'm trying for academics job as a professor, like there should be minimum 6.5, like in India.
Hmm.
But outside,
Oh,
it doesn't matter. It doesn't matter. Just my profile matters, like how many publications I have done in PhD, how many postdocs I have done. So that thing matters outside. Yeah.
yes. Even yes, similar thing. Like in India, they tend to put very concrete things. This what I saw.
Mhm.
Even while Mercedes tried to recruit, Uniaco didn't put any uh, grade cap because the founders themselves were from IIT Roorkee and they themselves had low grades. It would have been counterintuitive, but but Mercedes had a cap, like a hard cap of 6.5 something. And then I
Okay.
talked to them, and then while recruiting for IIT Roorkee, before I came to IIT Roorkee, we had a recruitment dive. and I talked to them and reduced it because you never know. It could be a person from chemistry department who's coming for data science. It doesn't matter what grades they got in like inorganic chemistry in first year, right? So I
Yeah.
tried to change that. But yeah, grades are important in generally, unfortunately or fortunately.
Yeah, especially in countries like India and in developing
Yeah.
countries. Yeah, it matters. Okay, Neeraj, thanks for your time, and I would like
Yeah.
to thank you for your post that this
Yeah.
talk was really informative for me also
And
and for the students, I'm sure.
yeah, I think someone tried to ask a
Join.
question, right? Um,
Yeah, there is a question. Yeah.
yeah, Siddhant, he asked, should you should you take MS after BTech? Yeah, this is what I told. After B, after the end of BTech, you're still like a reinforcement learning algorithm which has just been initiated. Your weights are almost random. As in, you're like me when I graduated, right? You also have interest in product analytics. You're interested in design or software engineering. Um, it's good to go into the industry after BTech, generally. Um, then try out some different things and then know the industry a bit. And once have very concrete goal that you want to do this industry only, and then you can apply for MS within that subject, within that industry. Otherwise, otherwise, maybe if you come freshly from BTech, you will still have a broad set of things. And in MS, you really have very less time to decide. First year, you will already be giving interviews for your first year internship. And in second year, you will have to get a job, right? So it's better to go to the industry and try out a bunch of things and then know the industry and then decide what you have to do have a very concrete goal and then go for MS. Yeah. Yeah.
Okay. So I think you answered Siddhant's question. Yeah. So last question from my side. I'm asking a lot of questions. So now, like you stayed 1.5 years in US. So what's your thinking now? Are you planning to settle there only, or you think you're coming back to India?
Yeah, I've invited my parents also in this. I think they are the two extra external participants here, I guess. Yeah, I'm a single son for my parents. So maybe if there is not any long-term possibility of them being here or them frequently visiting here,
Mhm.
I'm thinking maybe after 5 years or something, I will eventually come back to India. Yeah. So this is my current vision. Um,
Okay.
but yeah, I don't know what life has to offer. But one good
Mhm.
thing I am thankful for is I was in the industry for a while, tried a bunch of things. So I have to decide less on before. I don't have to think much about what I have to pursue. Instead, I just apply. And that's how I got my
Yeah.
internship immediately after coming here. So
Oh,
that was
that's
helpful.
amazing. Yeah,
Yeah.
that's amazing. And you clarity came with time, I think in your case also.
Yeah. Tried a lot of things. It's like your if any one of you have done reinforcement learning, you know what I'm talking about. Yeah. Uh, since you're data science students, I'm telling you this. Yeah.
Yeah. So, okay, Neeraj, thanks for your time. Uh,
Mhm.
we
Yeah,
we
thank you
decided,
very much.
yeah, we decided for 1.5 hours, but it's around 2 hours. But thank you very much. I think your talk was really informative and very encouraging for the students.
Yeah. Thank you very much, and thank you all the students for participating and listening to me for 2 hours. Thank you, Tina ma'am, for making this possible. I hope I'll meet you someday in Roorkee or elsewhere. Yeah.
Sure,
Thank you.
sure. Let us know when you are coming
Yeah,
here.
yeah, sure.
Thank
Yeah.
you. Thank you very much, dear students. And bye, Neeraj. Have a good night.
Bye. Yeah. Bye bye. Yeah, feel free to reach out whenever in LinkedIn or through email. Yeah. Thanks. Bye.
Goodbye. Bye.